Hi everyone. Addressing your feedback from today's lecture on buffers. Does the pH of a buffer always remain constant? What can change the pH of a buffer? So I think that question is in relation to the last question I asked, which is, if you dilute a buffer, how does its pH change? And we concluded that it didn't change. But in general, no, a pH of a buffer isn't constant. It will change if you add weak acid, or if you add strong acid or strong bases. The pH of a buffer is given by the Hasselbalch equation, the Henderson-Hasselbalch equation. So the pKa is referring to the negative log of the equilibrium constant for the weak acid. So that's a constant, but these concentrations, those can change. And if their concentration changes, then the pH changes. So the way you can do that, the way you can upset those concentrations, upset that balance, is to either directly add more weak acid, directly add more weak base, or convert weak acid into base, or convert weak base into acid by adding bases or acids. And this is what I was mentioning today. If I have a reaction where I add strong base to my buffer, the strong base reacts with the weak acid and produces the conjugate base and water. So the net effect when you add acid, or rather when you add, well, for that matter, when you add strong acid or strong base, and if you are adding strong base, you decrease the concentration of the weak acid, you increase the concentration of A minus. So this log becomes larger and larger as your numerator gets larger and your denominator gets smaller. This term gets larger, and so the pH increases. And that generally jives with what we would expect. If I have a solution and I add hydroxide ions to it, I expect the pH to increase. With a buffer, it does increase, just not by a large amount, only a little bit. Yeah. I was a little bit confused on the acetic acid sodium hydroxide example. I didn't understand that. Could you further discuss that? Yeah, certainly. So the reaction, the equilibrium that we were dealing with here, or the system we were dealing with, was a solution. Originally it was a solution of just weak acid, and the weak acid would be in equilibrium with its conjugate base. Some of it does automatically dissociate, transfers a proton to water, and produces weak base, but since the equilibrium constant for this reaction is relatively small, we assume most of the acid is in the acidic form, and I'll put A minus and I'll literally make it smaller to say there's a small amount of conjugate base present, but negligibly so compared to the protonated form of the weak acid. And so my question was, what happens if you add sodium hydroxide? If I add sodium hydroxide, how does that create a buffer? So generally speaking, a buffer needs to have weak acid and its conjugate base present. That's what makes it, those are the components of a buffer. And you technically already have that. A weak acid on its own technically is a buffer. There's a small amount of its conjugate base present, and so by definition, it's a buffer. It's not a great buffer because a great buffer has those concentrations in equal amount, and that's not the case for the weak acid initially. There's only a small amount of conjugate base present. But if I add acid, if I add base, the base reacts with the weak acid and converts some of it into A minus. And so by adding acid, you decrease some of your weak acid concentration, and you increase your conjugate base. You're going to convert some of this into weak acid, you'll lose some weak acid, and you'll generate some conjugate base. So that is how you are able to create a buffer by adding strong base to weak acid. Why did increasing the moles... Hold on, let me give you 1 second here. Along this line, in that last question, the most effective proportion of acetic acid to sodium hydroxide. Your question was, why is there only half of the hydroxide available? Why is there not the same amount? It's not so much that there is only half as much available. We were saying what proportion of base do I need to make the best buffer that I can. And remember, the buffer works best when the ratio of weak acid to weak base is about equal to 1. When I have equal amounts of conjugate base and weak acid. So I asserted the ratio that you want of weak acid to base was 2 to 1. Why is it 2 to 1? Why do you want half as much hydroxide as weak acid? Because again, initially we had no conjugate base. We needed to produce it. In fact, we wanted to produce enough conjugate base such that there would be an equal amount of weak acid. So what I want to do is convert half of the weak acid into its conjugate base. If I have 2 moles initially of weak acid and I add 1 mole of weak acid, well, this was going to be a limiting reactant problem, and the hydroxide ion is the limiting reactant. So I have 2 moles of HA with going to, and I know that there's going to be 1 mole, wait a minute, let me sure I'm getting this right. We have, how do I want to say this? You are going to, damn it, I'm screwing up on my my stoichiometry here. That's embarrassing. I want to know, okay, if I'm using 1 mole of hydroxide ion, I know that there is a mole ratio of 1 to 1, 1 mole to 1. 1 mole of hydroxide reacts with 1 mole of HA, so I will react away 1 mole of HA, so this one will drop down to, this guy will drop to 1 mole remaining. So if I have 1 mole of hydroxide and 2 moles of weak acid, they react in a 1 to 1 mole ratio. I'll react 1 mole of HA, produce 1 mole of A minus, and be left with 1 mole of HA. So again, the idea is I want to convert half of the weak acid, so I need half as much base as I have weak acid, because that's how I'm creating my conjugate base, is by the addition of a strong base. Okay, so this is on a previous question I had. Why did increasing the moles of hydroxide ions have no major effect on the ratio of, so let me write this out here. So you had this, that you had, minimal effect on the mole ratio of HA to the moles of A minus. That had minimal effect, but it had a much greater effect on the hydronium concentration. Okay, so we need to differentiate here. There were two examples I was looking at, two different solutions. One was a solution of a buffer solution, and the other one was just water. And technically there's some hydronium and hydroxide dissociated in water, but it's basically just water. For the buffer, specifically for the buffer, the hydronium concentration is determined by the equilibrium between the weak acid and its conjugate base. So that ends up being equal to the Ka times the weak acid concentration over the concentration of A minus. For just pure water, a different equilibrium controls it. For just pure water, the hydronium concentration is determined by the autoionization reaction, in which case it should be equal to Kw times 1 over the hydroxide concentration. So again, this one was for an equilibrium between a weak acid and its conjugate base. This one is between an equilibrium of water and water acting as acids and bases. So why is it that when you add hydroxide to the buffer system, that doesn't upset the hydronium concentration, but it does upset it for just pure water? Well, for pure water, you might be able to immediately see why adding the hydroxide changes the hydronium concentration. It's because the hydronium concentration is inversely proportional to the hydroxide concentration. That we can assert just from the autoionization of water. For the buffer, though, the hydronium concentration doesn't depend directly on the hydroxide concentration. Instead, it depends upon the proportion of the weak acid and its conjugate base. That proportion is upset. It is disturbed by the addition of hydroxide, but it's disturbed in such a sense that, well, this guy is going to increase by however many moles of hydroxide I add, and this one is going to decrease by however many moles of hydroxide I add. And that ratio ends up being a little bit less susceptible to changes than this one does. So it's a mathematical issue. Is that there's a chemical issue and there's a mathematical issue. The chemical issue is that for a buffer, you have a completely different set of reactions that govern the pH as opposed to in water. So in water, it depends directly on hydroxide concentration. In the buffer, it depends upon the concentration of the weak acid and its conjugate base. So that is one reason. The mathematical reason is that, okay, for hydronium, for weak acid, again, it is inversely related. It goes as 1 over the moles of hydroxide. Here it goes as moles of hydroxide over moles of hydroxide. So it's actually not a clear-cut linear or inverse proportionality. It's a little bit more complicated, and it will shift considerably if the moles of hydroxide becomes quite large. That's why we frequently will say that a buffer is resistant to small additions of strong acid and base. If you add a lot of base, you'll increase this denominator and you'll decrease this numerator, and then you really will drop the pH you will drop the hydronium concentration quite a bit. Is there a difference between HAC and HA? Yes and no. We use HA to refer to any weak acid, and HA dissociates into its conjugate base A minus and hydronium. This is a shorthand I have for acetic acid, which is also a weak acid, and it will dissociate into. Here, I'll show that as a reaction here. Into acetate and hydronium. So it's behaving like a weak acid. So in some sense, this expression is equivalent, but this one is specifically referring to acetic acid, and I'm just writing it as HAC as a shorthand, as opposed to writing out the entire chemical formula, and I've sort of tried to set it up so to be sort of analogous to what I would do for the generic expression, the generic molecular formula for a weak acid. So yeah, this one is general for any weak acid. This one was supposed to be specifically for the weak acid, acetic acid. Okay, ice tables are still confusing me. Could you go over those a little more? I won't go over them in this feedback video, but I do have a separate lecture video posted on the Brightspace website. It's in the lecture videos section where I go through some ice table calculations on equilibrium. So if you'd like to see some more examples of that, working through that, I would say check that. Even better, come see me in my office. I'm here most of the time, and I'd be happy to work through some example problems with you. Is there a study guide or are there practice tests available for the midterm? I will put together a short study guide. At the very least, I will just say these are I've done this before where I basically give a full study guide. I don't think I'm going to do that this semester simply because I think it will, the danger on that is then I feel somewhat, I don't want people to think that they'll only be tested on what's on the study guide. So I will give a list of sections from the textbook that I think are valid to be tested on. And I'll try to be as detailed about that as I can. As far as the types of questions I can ask, I would say see the homeworks, see the suggested problems. Definitely more the homeworks and the quizzes that I've given are more representative of the types of questions I like to ask. As usual, you saw in the first midterm, I tend to ask even just basic definition style questions, so I expect people to know some of the key definitions, some of the key terms from the chapters we've covered. As far as practice tests go, I don't have any practice tests available for people to work on, but I will suggest, and this is a suggestion I make to anybody who comes into my office asking for tips on studying, I will suggest you make your own practice test. There's nothing to stop you from doing that. I have given a list of suggested problems from the textbook. I would suggest that you take a selection of those problems, maybe 5 to 10 problems, however many you feel like you can get done in an hour-long period. Type them up in a Word document, format them like an exam, close the door, set a timer, and take it like an exam. And use that to prepare. You are just as capable of finding challenging acid-base problems or equilibrium problems. So I would say do that, encourage your friends to do that, then you can switch exams and you get practice tests that way. So there's that. And one last suggestion somebody made was it would be helpful if you start numbering your example problems, because it would be kind of confusing when you switch between problems and I don't know when you've finished a problem and when you're going on to the next one. That's a good suggestion, and I will try to start doing that. I admit I've been somewhat lax on my attempts to start to number the boards. I do that. I haven't been as consistent about that as I should be. I will try to start numbering my example problems to make things a little bit clearer for people. All right, so that is it for the feedback from today. Again, please remember to vote in the doodle poll. I'm still waiting for about 10 more people to vote. 10-ish so people to vote. At the moment, again, Mondays is still winning by a small handful of votes. So please make sure you vote ASAP for that. And I will see everybody on Monday.